Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about Stirling Engines. So let's dive right into it. Well, first we have to understand what the heck we are talking about. We are talking about an engine that is designed by Robert Stirling. That is why the name Stirling engine. And it is a kind of old system because it was built in 1816, basically the patent year. So you get the idea, like this is an old technology. And the early days, people thought this technology will replace steam and will become the foundation of industrial revolution. That did not happen, but there were reasons behind it. Now, this machine inherently does one thing. It takes heat energy and turns it into mechanical energy. Now it's kind of independent from heat source. Basically, you can take heat from anywhere. You can have run this from a hot spring, you can run this from coal, you can run this from wood, you can run this from nuclear. It does not care. As long as you have hot source, it will work. And it works on any heat system. That's the whole point. And because it's a closed loop system, like how steam system is closed loop, you do not burn coal in water. Like how jet engine is working, every system is exposed. You take air in, you burn fuel in that air, and then you get the work out. That's an open air system, like how your car engine works. Basically, you take air in, you mix petrol, and you seal it up, then you blow it up, and that's how it works. So those are what we call open system. This is a closed loop system. Nothing interacts with the outside world. So that is why it has the flexibility of taking any heat source. So how does it actually work? Now, in terms of working, it works on simple principle of if you heat a gas, it expands. That's all there is to it. Like you take a gas, you expand it. Either you can mechanically expand it or you can heat it. So we heat it, then we extract the mechanical work out of it. That's all we are doing. Now it reads temperature gradient. So basically, you're gonna have a cold side and hot side and cold side, hot side and cold side. You always need gradient. Now this gradient, you may see many people showing this kind of Stirling engine working on ice. So is it working on coal? Technically, yes, and practically no, simply because all that is happening is heat, the sides have been inverted. Basically, where you put ice, that became the cold side, and the ambient air became the hot side. So that's all it was. It needs temperature gradient. Now, depending on your design, you can have very high temperature gradient, or depending on your requirements, you could have very low temperature. Like for many industrial energy recovery system, people want low kind of heat, low quality heat, as they say. That is around 100 degrees Celsius to 200 degrees Celsius. That's like waste heat kind of territory. But you want an engine that works in that point. Like you can't expect steam turbines to work at that temperature. Steam generally works at 400 to 500 degrees Celsius. So for that reason, the temperature gradient is a very crucial aspect of it. And there are many gases that are used, simply because if you use air, you are technically using nitrogen mainly, but because of the mixture, the gas do not behave in sync. Basically, carbon dioxide will behave a bit differently than the nitrogen. So to make the engine as compact as possible, it's not necessary, but if you want your engine to be compact, you generally have to use a gas. And because gas is completely sealed from everything, basically you do not have like, okay, petrol is gonna go inside, so you do not have to worry about contamination, lubrication, and all that jazz. So they can last, these Stirling engines can last for a very long time. And there are three primary configurations of this. Configuration number one is alpha, where you have hot and cold completely independent. You're like a V block design. Then you take beta, which has hot side and cold side parallel to each other, and many times they could be literally working inside each other. So you can have like hot side that is working inside, and you can have cold side that are working on top. So this design is generally used where you have to make your system small. Now if you have the luxury of size and weight, people generally go with alpha systems. But if you do not have luxury of alpha, you go with beta. Now what if you have to work on low thermal expansion, basically very low temperature gradient? Basically your exhaust heat is, let's say, 100 degrees Celsius, and ambient air, let's say you are in India, that's around 50 degrees Celsius, or even 60 degrees Celsius. So you only have to work with 40 degrees Celsius of gradient. So generally gamma designs are used. Gamma designs generally use huge crystals, so it can extract energy out of it. They're not very powerful, but they work. They work from very low gradient. That is why all the designs that you see on Amazon or eBay, they are generally gamma designs, simply because again it works on very few degrees Celsius gradient. Like you can literally have a 3 to 5 degrees Celsius gap and it will still work. Again, do not expect torque out of it, but it will work. So this is the working of it. Basically, you heat a gas and gas physically moves. Now, extracting that movement using steam design, basically piston designs, you get the rotational energy out of it. And depending on what you want to do, in early days, people wanted to run air compressor of air, refrigeration compression out of it, and locomotions out of this. So that's up to you. Nowadays, you want to run generators of this. So how the heck it's actually built? Now, in terms of buildings, you have to think differently compared to a turbine, compared to a combustion engine, you have to think external heat source. So where can you get that heat depends on you. Like many scenario, like this was a generator made by Philips. I provided the video down below. Sorry about the bad quality, because again it was like 10 years old, and the generator itself is like 30-40 years old. So it had a burner, and it's completely open burner, like you just have a flame that is now you may think, wouldn't that cause pollution? Actually no, that's the good part about it, because if you are not exploding everything, basically like you're taking air in, compressing and exploding it, you do not get too much NOx emission. So having an open flame has that benefit, and continuous open flame, it does produce the same amount of carbon dioxide that you will get out of a combustion engine, but you do not have that much NOx emissions. So people actually like this idea, and it's kind of environmentally friendly, but it's exposed system. You do not have like hot exhaust fan. You could literally have flame coming out. Ideally most of the heat energy would have been extracted by the engine, but again nothing is 100% efficient. So you have to design the hot side to be completely independent. You just have to heat something, and gas should basically there should be a very solid barrier. The gas that is working inside should not leak out. Now this system, Philips generator, was designed to work on air. That is why it's not very successful. But when you talk about Stirling engines that nowadays are used in solar concentrated heat systems, they generally work on nitrogen or helium. Sometimes people have tried hydrogen. Hydrogen is the best scenario case, simply because hydrogen is light. So you have 100 degrees Celsius of energy. It takes that 100 degrees Celsius and travels very fast. So it can, let's say, reach 100 basically kilometer per second. But you have carbon dioxide, it will barely go to 75. You have nitrogen, 80, 85. So people, that's why people want one gas. Hydrogen is the best. Side effect, hydrogen does not like metal. It can literally go through the crystal lattice of metal. So you have leaking, and not to mention hot hydrogen leaking is really not a good idea. So people really have moved away from hydrogen. They want it. Like if you want absolute power density, people will go with hydrogen. But if you have want to make sure your system keeps running for years and years without going boom, people generally like, yeah, let's not use hydrogen. Generally helium can be chosen, but helium is even more expensive than hydrogen. Again, it's safe, but it's dangerous in terms of like cost wise. It's bad for your bank account. So people have finally settled to nitrogen. It's easy to extract from the atmosphere, super cheap, and it works well enough. It's compared to air, it's better. So you have hot side that allows the gases to expand. Then you have cold side that compresses the gas, because again the gas system is sealed, so you cannot just keep expanding it. It will expand to vacuum. So the cold side has generally radiators, and that's how it works. And the working fluid is generally interconnected. That's the whole point. You cannot have anything coming from outside or going into inside. The contamination must be avoided. So what are the problems of this? This system is sealed, works on any heat source. It's efficient compared to steam systems. Then why the hell it does not it's everywhere? The problem is it works best in constant power. So basically you want a generator set, but your generator has to adapt. Basically, let's say you are running a generator set and you started to, hey, I'm gonna turn on the AC, power load goes up. Your generator is like constantly compensating for that. Now again, you turn off the AC, it's like, okay, goes down to all that. So your generator is handling the fluctuation. This puppy does not like that. It's like, give me a constant load. Basically, put me into the grid. I'm gonna give you whatever my power rating is. Let's say 25 kilowatt. I'm gonna keep dumping 25 kilowatt without changing. So it likes to stay in that kind of scenario. It's like, I'm gonna give you 25 kilowatt. That's it, done. It works flawlessly. But if you want to, like a petrol engine, how you have in your car, you press the accelerator, it's like boom boom. You do not get that boom boom performance here. So even though NASA did build an actual car out of Stirling engine, it even though it quote unquote performed equivalently, it never caught on, because to achieve that kind of oomph out of it, they took too much too much engineering was spent on that. Then it has low starting torque. Inherently an engine should have very high starting torque, but this puppy is like very bad in that regard. So if you have to run a compressor directly, you may need a starter motor to just keep the system going. Then at that point Stirling is just like, I got this, but again it requires a starting system. Low power density. That is why every Tom, Dick and Harry wanted to use hydrogen in the beginning, because again this is a big steam turbine. Now this puppy can produce upwards of, let's say, 300 megawatts. That's a lot of power. Now what will happen if you want to get 300 megawatts out of even a hydrogen based Stirling engine? It would be 10 times bigger than this. That's the whole point. That is why like you will never see this used. It's just too huge. It becomes ludicrously huge. So low power density is kind of like a bottleneck, because again you have to think about how the heck you're going to transport it. And then the final nail in the coffin, simply because it's a reciprocating engine, aka it goes like this. You do not want that. Basically, whenever that happens, a reciprocation engine happens, you are fighting your own inertia. It's like you compress the air, you compress the basically fuel in it, you fire the spark plug in it, boom, like okay, explosion happened. You got the chemical energy. What is that energy doing? It's trying to push you back. Again, your crankshaft is trying to extract that energy. Everything is awesome, but here's the what happens when it starts to go up? Like you are stopping something that you yourself dumped energy into. So you are fighting the energy that is there, and then you're like going back, fighting, going back. That wastes inherently a lot of energy. Now compare that to steam turbines. Nothing. It's just like constantly flows. What about jet engine? Jet engines are the best case. Basically, air comes in, it gets compressed, it burns, and exhausts. No big spam. It's like smooth flow. Energy efficiency is higher. People want high energy efficiency. You do not want to burn like hundreds of tons of coal if you don't have to. So that's the reality. The inherent limitation of the it's not that power dense. On top of that, if you want to make hundreds of megawatt out of it, it's generally not suitable because these designs will not inherently it will not last. So these are the inherent limitation. So what we can expect in the future? Now, because of the military's budget, Sweden built something very interesting. Sweden built a submarine engine out of this. Now, the benefit of that, they achieved a level of stealth that was so horrifyingly high that during one of the what we call simulated war games, they actually crossed the blockade of a U.S. naval force which had nuclear submarines on them, and nobody could detect it, and they directly went, bottom of the main aircraft carrier. It's like that again. They did not fire an actual torpedo, but that they showed it like, yeah, we could do this. My question is like, how the heck this could be so silent? Simply because it was running on Stirling engines. Stirling engines are inherently quieter than diesel engines, where you have like pish, tick, 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 tick. You don't have that, so inherently silent. What about nuclear submarines? Nuclear submarines have giant nuclear reactor. Those reactor requires constant coolants, and those things require a lot of turbine. So basically, there is a background noise of the system itself that will create a certain level of basically, I will call it a, let's say, a band where you cannot hear, simply because that's your own noise. This puppy is quieter than that, simply because for the cold side they have the whole sea as a heat sink. So they utilize basically fuel, diesel, and liquid oxygen, so they can burn for limited amount of time internally also. So they do not always have to come up for the air. They can come up in the air and they easily breathe, but if they have to be like, okay, still and still need power, they can do that. That's why they carry liquid oxygen also. So it was quite amazing. Like it's so small, like you can say this is not like a huge thing, but it works. It's stealthy as hell, and it freaked the hell out of them. Like, it's like, what the hell? It's like we have nuclear submarines, and you're like, pick. So a lot of interest, and again, military budget. So the size and complexity does not matter. Like you just get the money. So a lot of interest after this, war exercise poured into this system. And then you have to most common use that people know of Stirling engine is basically solar dish power. You have dish, you have solar, and that works. Now the reason why it's not popular everywhere, even though inherently it has more power density. So basically your land wise, it's not put and forget. People want something that they can put and forget. Solar panels are like that. Put and forget. Don't even think about it. Like you do not have moving part. Best case scenario, you have to worry about your inverters, which will good quality inverters can easily last for 5 to 10 years, easily. So that is why even though the Stirling systems are more powerful, they do not work that well, simply because people don't want to buy that. Like you don't want to buy something and you have to figure out like, okay, I have hundreds of moving tracking system, then I have a whole engine that is moving and all that. So it's not that successful, but it's there. Like more than enough people are using it. Then we come to thermal battery. If you have watched my video about thermal battery, nowadays people want to achieve what we call flow battery. Basically the batteries are in a molten state. Basically thermal battery, you take let's say graphite and silicon, you melt it at 1500 degrees Celsius. So how do you extract energy out of it? You just have thermal energy. Stirling engine, it's more efficient, and the scales that we are talking about is like 5 kilowatt, 10 kilowatt. Stirling engine is quite efficient. On top of that, Stirling engines have always been looked at. Like nobody ever abandoned Stirling engine, even with all the problems. They always like, dude, it has potential. So nowadays that potential is starting to shine. That is combined heat and power. I have provided a link and PDF from a company down below, and this company is specifically making a Stirling engine that is upwards of 25 kilowatt. And the selling point of that is it works on low grade heat. You can have like, there are many hundreds of industry, be it from clothes manufacturing to food manufacturing to dye manufacturing, like hundreds of things that actually does thing, but they have a lot of waste heat. That waste heat can be recuperated in electrical energy if Stirling engine works. So this company inherently built a engine that can run on waste heat. Selling point, it works as very low heat, as in like as low as 100 to 200 degrees Celsius. There are many scenarios where your waste heat is like 500 degrees Celsius. So it's amazing. Like people are rushing into that system. Let's see how it unfolds, because combined heat and power is the next evolution. Basically, if you want to make sure you get more than 50% out of your fuel, just do combined heat and power. And it's not even limited to, like, let's say you may be like, okay, the hot side I can run hot water heater. In winter places, like cold places like Sweden and all that, Germany and all that, you may be like, dude, that's amazing. But in India, you're like, what the hell? What I'm gonna do with hot water? My outside temperature is 55 degrees Celsius. So we can run air condition on that using something known as absorption chiller. So you can run air condition directly on the thermal waste energy. So your total efficiency could be much higher. You can achieve 70 to 90% efficiency. So that's the whole point. CHP is very attractive nowadays, simply because, again, you don't want to burn fuel if you don't have to. So there is a lot of potential into this. It's never gone. It's like, clinging on to it. It's like, I'm gonna be there someday. So a lot of interest in that, especially after the submarine. So this was my presentation on Stirling engine. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, you didn't enjoy it, I'd urge you to press dislike, press it twice to show me extra disappointment, and please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.